In April 2024, 31 million Americans stood inside the moon's shadow. Next week, almost none of them will. On August 12th, the moon covers the sun completely over Greenland, Iceland, and northern Spain. In the United States, the best you can do is a bite. Maine and the far northeast get somewhere near a fifth of the sun. Alaska does better. Half the country sees nothing whatsoever.
And the standard explanation is that eclipses are rare, and the Earth is mostly ocean, and America got lucky twice in 7 years.
That explanation is wrong. Not the facts, the framing. Because the eclipse skipping America next week is not unrelated to the one America is waiting for. It is the same eclipse, 18 years and 11 days apart, member 48 and member 49 of a family that has been running since 1179. That family gave America a coast-to-coast totality once already, and in 2044, over Montana, it will cast its last shadow on Earth. Eclipses are not events, they are members. Every total eclipse belongs to a numbered family that runs for roughly 1,200 years, produces 70 or so eclipses, and then dies. The one arriving this month is number 48 in a family called Saros 126. It began in 1179. It ends in 2459. And in all that time, 1,280 years, it produces exactly 10 total eclipses. You are alive for the last 2. The family is walking north and west. In 2008, it crossed Siberia and China. This month, it crosses Greenland, Iceland, and northern Spain. In 2044, it comes down over northern Canada and stops at sunset over Montana and the Dakotas. And then it steps off the edge of the world. On September 3rd, 2062, Saros 126 will cover 97% of the sun and produce no totality anywhere. Its shadow will pass above the pole and miss the planet entirely. It will keep missing every 18 years for another 4 centuries. So the 20-year wait is not bad luck. It is the last act of something that started before the Magna Carta. And to understand why it ends over Montana, you have to start where it begins this month, at midnight on the roof of the world. At 11:59 at night, on a peninsula in Arctic Russia where almost nobody lives, the sun comes up. 4 minutes later, it starts going out. That is the first contact of the total solar eclipse of August 12, 2026. Not in Iceland, not in Spain, here on the Taimyr Peninsula at 1 minute to midnight on a coastline that has no permanent settlement for hundreds of miles in any direction. Every total solar eclipse begins at sunrise somewhere and ends at sunset somewhere else. That is not poetry, it is geometry. The moon's shadow can only touch the Earth where the sun is above the horizon. So the shadow's track has to start at a place where the sun is just clearing the edge of the world and finish at a place where it is just leaving. But this far north, in August, sunrise is a technicality. Above the Arctic Circle in summer, the sun circles the sky without properly setting. It dips toward the horizon, grazes it, and climbs again. So, the moment the almanac calls sunrise happens at 11:59 at night, and the eclipse that will eventually darken northern Spain begins in something that isn't really night and not really morning either. Then, the shadow moves. And this is where the eclipse of 2026 stops behaving like the ones you have seen. Most eclipse paths run roughly west to east across the middle of the planet. April 8, 2024 came ashore in Mexico, crossed Texas, and left over Newfoundland. August 21, 2017, ran Oregon to South Carolina. Both of those tracks are the shape you expect, a long diagonal band sweeping left to right somewhere in the populated middle latitudes. This one goes north. The path leaves Russia almost immediately, loops over the top of the planet, and drops down onto the eastern coast of Greenland. It does not cross the equator or the tropics or any part of the world where the most of the 8 billion of us live. It draws a curve over the roof of the Earth and comes down the other side. The strip of ground where the sun goes completely dark is called the path of totality, and the word path oversells it. It's a stripe. For this eclipse, it's about 183 miles wide, which sounds enormous when you set it against the 7,918 miles of the Earth's diameter. Picture a garden hose laid across a football field. Stand on the hose and you see the corona. Stand 1 field away and you see a bite out of the sun and nothing else. Everything about this film comes down to where that stripe falls. So follow it. It falls first on eastern Greenland. Scoresby Sund, one of the largest fjord systems on Earth, sits inside the path. It's a place with a population you could fit in a school hall, reachable in practice by ship or by charter flight, in a part of the world where August weather does what it wants. A handful of eclipse chasers will be there. Most of them will have been planning it for a decade. Then Iceland. The path clips the western edge of the island and eclipse it in the one place that matters, because totality will be visible from Reykjavik, an entire capital city inside the shadow. That is the rarest kind of luck in eclipse geography, and it is the reason Icelandic hotels sold out years in advance. And then, for a while, nothing. The shadow crosses open Atlantic, and this is where the eclipse is at its very best. The point on Earth where the moon's shadow axis passes closest to the center of the planet is called greatest eclipse. And for this one, it lands at 65 degrees north, 25 degrees west, out at sea. Maximum duration of totality, 2 minutes and 18 seconds. 2 minutes and 18 seconds is not long. The eclipse most Americans remember, April 2024, ran to 4 minutes and 28 seconds at its best. 2026 gives you barely half of that, and it gives the longest slice of it to seawater. The last land it touches is Spain. In Burgos, León, Valladolid, and Soria, totality runs somewhere close to 1 minute and 45 seconds. The path continues southeast across the peninsula, brushes a small section of Portugal, and exits over the Mediterranean and the Balearic Islands. And it does all of that with the sun almost gone. This is the detail that will define every photograph you see from this eclipse. In Spain and the northwestern tip of Portugal, the sun will not be fully covered until late evening, shortly before it sets. Spanish observers are not going to get the classic overhead black disk in a dark blue sky. They are going to get a black sun sitting low, in a sky that is already orange at the rim, with the corona hanging over a horizon. Astronomers have a slightly grudging word for eclipses like this: a grazing geometry. The moon's shadow is not slamming into the middle of the daylight side of the Earth, it is skimming the upper edge of it, catching the planet at a shallow angle, which is why the track curls over the pole, why the sun sits so low everywhere along it, and why totality is only 2 minutes and 18 seconds at its absolute best. So here is the shape of August 12, 2026 in one sentence. It begins at midnight on an inhabited Arctic peninsula, runs over the North Pole, comes down through Greenland and Iceland, spends its finest moment on empty ocean, and dies at sunset over Spain, having spent almost its entire life above the 60th parallel. It is the first total solar eclipse for mainland Europe since 1999. 27 years of waiting, ending in a Castilian evening. Which raises the obvious question, and it is the question this entire film is built on. That track spends its whole existence in the high north, 65 degrees, 70 degrees, 75 degrees north. There is a great deal of North America up there. Canada reaches past 80 degrees. Alaska sits above 60. Greenland, which the shadow crosses in full, is closer to Baffin Island than London is to Rome. The moon's shadow passes within a few hundred miles of North American soil on August 12th and does not touch 1 square foot of it. Not in Canada, not in Alaska, not anywhere in the lower 48. And the reason it misses is not that it came close and got unlucky, it's that it was never going to.
If you are standing in Phoenix or Los Angeles or Atlanta or Dallas on August 12th, here's your complete experience of the total solar eclipse of 2026. Nothing. The sun does not change. There is no eclipse there at all. The moon's outer shadow reaches only the northern tier of the country. 25 states see a partial eclipse. The other 25, including the entire South, the Southwest, the West Coast, and the Pacific Northwest, see nothing whatsoever. That is worth sitting with for a second because it is not the picture most people have. There's a general sense in the United States that an eclipse is something the whole country half participates in. That was true in 2017. It was true in 2024. It is not true this time. So who does get something? Only observers east of roughly mid-Ontario in Canada and northeast of a line drawn between New York City and Rochester in the United States will see more than 10% of the sun covered by the moon. 10%. That is the threshold for the good part of the contiguous United States. The best position in the lower 48 is the far northeastern corner, Maine, New Hampshire, Vermont. Northern Maine does best of all, up around Presque Isle and Caribou, where the figure lands somewhere in the high teens to low 20s. I want to be careful with that number because the published figures disagree with each other by several percentage points depending on which source you read, and this channel does not round in whichever direction sounds better. Call it a fifth of the sun in northern Maine, less as you move south and west, 0 once you cross that Rochester line. Alaska does better than any of them. Anchorage reaches somewhere around 28% coverage, and the Aleutian chain, stretching further west and sitting closer to the shadows track, does better still. There's a clean logic to that. The path of totality runs across the top of the world. The nearer you are to the top of the world, the nearer you are to the path, and the deeper the bite you get. Alaska is simply closer to the action than Alabama. The timing follows the same north and east logic. In northern Canada and Alaska, the eclipse starts and ends in the morning. Canada's eastern provinces get it in the afternoon. In the northern contiguous United States, it begins around midday and lingers into the mid-afternoon for those further east. So this is not a dawn or dusk event for North America. The sun will be high, conditions will be good. And what those states will see, in NASA's own phrasing, is a small bite taken out of the solar disk as the moon appears to just clip the sun. Now, if you're in that northern band and you intend to look, there's one non-negotiable piece of housekeeping, and it takes 10 seconds. A partial eclipse is not safe to look at, ever, at any percentage, at any moment. Totality is the only phase of any eclipse where the naked eye is safe, and no part of North America gets totality on August 12th, which means there is no second on that entire day when it is safe to look at the sun without a certified filter. You want glasses carrying the ISO 12312-2 standard. Sunglasses do not work. Exposed film does not work. A welding shield below shade 14 does not work. A pinhole projector onto a sheet of paper works perfectly and costs nothing. That is the safety brief. It will not come up again. Because here is the part that reframes everything, and it is the reason this film exists. If you stand in northern Maine on August 12th with a fifth of the sun covered by the moon and you do not have eclipse glasses and nobody has told you an eclipse is happening, you will not notice. Not you might not notice, you will not. The light will not visibly dim,
Shadows will not sharpen in any way you would clock. The temperature will not drop. Birds will carry on exactly as they were. It will be an August afternoon. The reason is your own eyes. Human vision does not measure light, it adapts to it. And it adapts across an enormous range. You can read a newspaper in bright sunshine and read the same newspaper under a streetlight, and your brain reports both as simply light enough. That flexibility is the single most useful thing about your visual system, and it is completely ruinous for noticing a partial eclipse. Take away 20% of the sun and your pupils quietly compensate before you have finished the thought. Take away 50% and the day looks at most faintly overcast. Even at 90% covered, observers in 2017 described conditions as something like heavy cloud or an odd metallic quality to the light. And plenty of people who were not looking up went about their day and missed it entirely. And then, in the last fraction of a percentage, the whole thing changes character. That final sliver of sun is the difference between an interesting afternoon and the thing 31 million Americans stood outside for in 2024. The corona appears, stars come out. The horizon goes the color of a sunset in every direction at once, because you are looking out from under a shadow that is only 100 and some miles wide, and you can see daylight beyond its edges. The temperature drops. Animals behave as though night has fallen, because as far as they are concerned, it has. So the honest answer to what does America get on August 12th is this: half the country gets nothing. The other half gets an event that is real, measurable, photographable through a filter, and functionally invisible. A partial eclipse is not a diluted total eclipse. It is a different phenomenon. There is no sliding scale, no 90% of the experience at 90% coverage. There is everything inside a stripe of 183 miles wide, and there is essentially nothing outside it. Which is why the weight matters, and why the number attached to it deserves one piece of precision that gets left out of almost every article you will read this week. Alaska gets a total eclipse in 2033, 11 years from now. Anchorage, Nome, Arctic coast, real totality on the 30th of March. So America waits until 2044 is not quite true, and this channel is not going to pretend otherwise for a cleaner headline. The lower 48 waits. Totality returns to Montana and North Dakota in 2044. Alaska gets there first. But that only sharpens the question. The shadow spends August 12th crossing latitudes above 60 degrees north, and Alaska sits above 60 degrees north, and it misses Alaska anyway. Something is deciding where that stripe lands, to the mile, and it's not luck.
Hold a coin up to a lamp and look at the shadow it throws on the table. There are two shadows, not one. There is a small, hard core where the coin blocks the bulb completely, and around it a much larger, soft ring where the coin blocks part of the bulb and the rest of the light gets past. Those two regions have names, and they are the whole story of why half of America sees nothing on August 12th. The dark core is the umbra. The soft ring is the penumbra. The moon throws exactly the same pair of shadows. Its penumbra, the region where the moon blocks part of the sun, is enormous. It is thousands of miles across when it lands on Earth, which is why the outer edge of it can cover Alaska, the Great Lakes, New England, all of Canada, and part of North Africa on the same afternoon. The umbra, where the sun goes out completely, is 183 miles wide. That gap between thousands and 183 is not a small design flaw in the solar system. It is the reason total eclipses are the rarest thing most people will ever queue up to see. And it comes down to a piece of geometry that is almost uncomfortably tight. The moon's umbra is not a cylinder. It is a cone, and it tapers because the sun is not a point of light. The sun is a disk about 865,000 miles across, so light spills around the moon's edges from every part of that disk and closes the shadow off into a spike.
That spike is roughly 232,000 miles long. And the Moon orbits at a distance that swings between about 226,000 miles at its closest and 252,000 miles at its furthest. Read those two figures against each other. The tip of the Moon's shadow only just reaches us. Sometimes it does not reach us at all. That is what an annular eclipse is. When the Moon is near the far end of its orbit, the shadow cone runs out of length before it arrives. The tip falls short, and what touches the Earth is the widening region beyond the point where a rim of sun is always visible. No corona, no stars. A ring of fire and a day that stays bright. So the Moon does not comfortably blot out the sun. It barely manages it, by a margin of thousands of miles out of 250,000. And when it does manage it, what actually lands on the ground is the last narrow inch of a cone 232,000 miles long. 183 miles of it. Now scale that against the planet. The Earth is 7,918 miles across and has a surface area of about 197 million square miles. The umbra at any given instant is covering a patch smaller than a mid-sized American state. And then it moves. The whole reason there is a path rather than a spot is that the Moon is traveling along its orbit while the Earth turns underneath it, so the shadow gets dragged across the surface at something over 1,000 miles an hour, drawing a band. The band is long. It is still only 183 miles wide, and when you total up the ground it covers, it accounts for a fraction of 1% of the Earth's surface. And most of that fraction is ocean. 71% of this planet is ocean. That figure is dull until you apply it to eclipses, at which point it becomes the single greatest source of frustration in the history of astronomy. The Moon's shadow does not care what it lands on. Most of the time it lands on seawater, or ice, or desert, or the parts of Siberia where nobody has ever built a road. This eclipse spends its longest and best moments, its full 2 minutes and 18 seconds, in the open North Atlantic with nobody underneath it. There is one more variable, and it is the one that will matter enormously in the last act of this film. The width of the path depends on the angle at which the shadow hits. Point a torch straight at a ball and you get a tight circle. Slide the beam toward the edge and the same amount of light smears out into a long stretched ellipse. The Moon's shadow does exactly this. When it strikes near the middle of the daylight side with the sun high overhead, the footprint is compact. When it strikes near the rim with the sun low, the footprint stretches. Which is why the 2026 path is 183 miles wide, even though totality only lasts 2 minutes and 18 seconds. It is a wide path not because the shadow is big, but because it is arriving at a slant. So here is the number this chapter has been walking toward. Pick any spot on Earth, your house if you like. On average, the Moon's umbra passes over that spot roughly once every 375 years. Not once a lifetime, not once a generation, once every 4 or 5 lifetimes stacked end to end. That is the true baseline. That is what should happen. And it makes what has actually happened to the United States look faintly ridiculous, because the lower 48 got totality in August 2017 and again in April 2024, 7 years apart, and will get it again in 2044 and again coast to coast in 2045. 4 total eclipses in 28 years in a country that statistically should be waiting centuries between them. So the complaint that America is being made to wait 20 years is, by the standards of the actual universe, close to unreasonable. The wait is not the anomaly. The last decade was. But none of that explains the precision. Not roughly 20 years, not sometime in the 40s. August the 22nd, 2044 over Great Falls, Montana, with the sun 15 degrees above the horizon. Somebody worked that out, and the method they used is older than the telescope. 0.8997. That number decides everything about the eclipse of August 12, 2026. It decides that the path runs over the North Pole. It decides that Spain sees it at sunset. It decides that totality lasts 2 minutes and 18 seconds instead of 6. And it decides that no part of the United States sees the sun go out. Astronomers call it gamma. There is one for every eclipse that has ever happened or ever will, and once you know how to read it, you can look at any eclipse in the catalog and know instantly, roughly, where on Earth it lands and how good it will be. Here is what it measures. Point a torch at a ball, straight at the middle. The bright spot lands dead center, tight and round. Now, slide the beam sideways. The spot moves toward the edge of the ball and stretches out as it goes. Keep sliding. At some point, the beam is clipping the very rim, throwing a long smear of light around the curve. Slide a fraction further, and it misses the ball entirely and hits the wall behind. Gamma is the position of that beam. Specifically, it is the distance between the axis of the moon's shadow and the center of the Earth, measured in Earth radii at the moment of greatest eclipse. That is a technical sentence, so here's the plain one. Gamma is how close the shadow comes to hitting the middle of the planet. Gamma of 0 means the shadow axis passes straight through the center of the Earth. The eclipse lands somewhere in the tropics, the sun sits directly overhead, the umbra hits square on rather than at a slant, and totality runs long. These are the great eclipses, the ones that give you 6 and 7 minutes. Gamma of 1 means the axis grazes the very edge of the Earth. Polar, grazing, sun on the horizon, barely an eclipse at all. And gamma above 1 means the shadow axis misses the Earth completely. The umbra passes over the top of the planet and touches nothing. Somewhere below, people see a partial eclipse from the penumbra, and nobody anywhere on Earth sees totality, because totality did not happen. So, 0.8977, 90% of the way from the center of the Earth to the edge. Everything in the first 2 chapters follows from that single figure, mechanically, with no other information required. A shadow axis that far off center can only strike the planet near the rim, and in this case, the northern rim, because gamma also carries a sign, and this one is positive, meaning north. So the path is polar. The sun is low everywhere along it because you are standing near the edge of the daylight hemisphere. The footprint is smeared wide by the shallow angle, which is where the 183 miles comes from. And totality is short because the shadow is skidding across the curve of the Earth instead of pressing into it. Compare it with the one Americans actually remember. April 8th, 2024 had a gamma of roughly a third of the weight in the edge, not 9/10, which is why the shadow came ashore in Mexico rather than Greenland, why the sun was high, and parts of that path got 4.5 minutes of totality instead of 2. Same phenomenon. Same moon, same sun. One number apart, and a completely different experience for a completely different half of the world. Now here is the part that makes gamma more than a filing label. August 1st, 2008. Gamma 0.8307. August 12th, 2026. Gamma 0.8977. August 23rd, 2044. Gamma 0.9613. Those 3 eclipses are 18 years apart, and the number is climbing. Not drifting randomly, climbing in the same direction by almost exactly the same amount every single time. 0.83, 0.09, 0.96. Gamma is not a description of an eclipse, it is a position on a slope, and these 3 eclipses are walking up that slope together toward the number 1, which is the edge of the world. Which is also incidentally why they land where they land, each one further north than the last, each one with the sun lower in the sky. 2008 had the sun 34 degrees up at greatest eclipse. 2026 has it at 26. 2044 will have it at 15. 3 eclipses 18 years apart, marching north in step, with the sun sinking toward the horizon a little further each time. That is not a run of coincidences. Those 3 eclipses are related to each other in a way that has a name, a catalog number, and a birth date in the 12th century. And once you know what connects them, the 2044 date stops being a prediction and starts being an appointment.
6585.3. Every total eclipse you have ever seen or ever will see is governed by that number. It is a count of days: 18 years,
11 days, and 8 hours. Wait exactly that long after any solar eclipse and another one happens, and it is almost the same eclipse. To understand why, you need 3 numbers, and they are the only 3 pieces of arithmetic in this entire film. First, for a solar eclipse to happen at all, the moon has to be between us and the sun. New moon. The time from one new moon to the next is 29.53 days, and astronomers call it the synodic month. That happens 12 or 13 times a year. If that were the only requirement, there would be a solar eclipse every single month, and obviously there is not. Second, the moon's orbit is tilted by about 5 degrees relative to the plane the Earth travels around the sun in. So most new moons, the moon passes above the sun or below it from our point of view and throws its shadow into empty space. There are only 2 points in its orbit where it crosses that plane, and those are called the nodes. An eclipse requires a new moon that happens at or very near a node. The time for the moon to go from one node back to the same node is 27.21 days, the Draconic month. Third, the moon's orbit is not a circle, it is an ellipse, so the moon is closer to us at some points and further at others. That decides how big it looks, which decides whether you get a total eclipse or a ring of fire. The time from closest approach back to closest approach is 27.55 days, the anomalistic month. 3 cycles, 29.53, 27.21, 27.55, all running at once, all slightly out of step with each other, none of them a neat multiple of the others. For a really good eclipse, all 3 have to line up at the same time. New moon at a node, with the moon close enough to cover the sun. And because the 3 periods do not divide evenly into one another, that triple alignment does not repeat on any obvious schedule. Except that it does, just not obviously. 223 synodic months come to 6,585.32 days. 242 draconic months come to 6,585.36 days. 239 anomalistic months come to 6,585.54 days. 3 completely independent cycles of the moon's orbit with nothing whatsoever to do with each other, all arriving at the same total within about a fifth of a day of one another. That is the Saros. It means that 18 years, 11 days, and 8 hours after any solar eclipse, the sun, the moon, and the node return to almost exactly the same arrangement, and the sky does the same thing again. Nearly the same duration, nearly the same type, nearly the same geometry. And this was known before anyone had any idea why. Babylonian astronomers working with nothing but records and patience spotted the 18-year rhythm in eclipse tables well over 2,000 years ago. They couldn't have told you about draconic months or orbital inclination. They simply noticed that eclipses rhymed and wrote down the interval. The word Saros was attached to it much later by Edmund Halley in the 1690s, borrowed from a Babylonian term that turned out to mean something else entirely. The name is a mistranslation, the cycle is not. So, Here's what that does to the way you have to think about eclipses. An eclipse is not an event, it is a member. Every solar eclipse in history belongs to a numbered family called a Saros series, and each series produces one eclipse every 18 years, 11 days, for over 1,000 years, then stops. There are dozens of these families running simultaneously, overlapping, which is why eclipses happen somewhere on Earth 2 or 3 times a year, even though each individual family only fires once every 18 years. They've been cataloged exhaustively. Every eclipse from 3,000 years before Christ to 3,000 years after has been calculated, assigned to a family, and given a sequence number in it. The total solar eclipse of August 12, 2026 is eclipse number 48 of 72 in the family called Saros 126. That family began with a small partial eclipse near the South Pole on the 10th of March, 1179. It will end with another small partial near the North Pole on the 3rd of May, 2459. 1,280 years from first to last, 72 eclipses long. The one crossing Iceland next week is the 48th of them, which means somewhere in that same catalog, on the very next line, there's a member 49. It has a date, a gamma, a duration, and a landfall, and all 4 of those things were calculated decades ago. The date is August 23, 2044. 18 years, 11 days, and 8 hours. That last part is the interesting part, not the 18 years, not the 11 days, the 8 hours. Because if the interval between 2 related eclipses were a whole number of days, they would arrive at the same time of day, and the same face of the Earth would be turned toward the sun to receive them. The shadow would land in roughly the same part of the world every time. Eclipse chasing would be a much cheaper hobby. But it is not a whole number of days, it is 8 hours over. And in 8 hours, the Earth turns 1/3 of the way around. So when a Saros family fires its next member, the geometry in space is nearly identical. The sun and moon and node are back where they were. Everything is as it was, but the planet underneath has rotated 1/3 of the way around. The shadow comes down in the same relationship to the sun and lands about 120 degrees of longitude further west. Every eclipse in a family is displaced roughly 1/3 of the way around the world from the one before it. Which is not a theory, it is written down in a column in the catalog. So let us read it. 1990, July 22nd, greatest eclipse at 169 degrees east. Finland, the Soviet Arctic, the Bering Sea. 2008, August 1st, 72 degrees east, the Canadian Arctic, Greenland, Siberia, and northern China. 2026, August 12th, 25 degrees west, Greenland, Iceland, the North Atlantic, Spain. 2044, August 23rd, 120 degrees west. 169 east, 72 east, 25 west, 120 west. Count the gaps. 97 degrees, 97 degrees, 95 degrees. The same step west every 18 years for 1,000 years. So the question that opened this film, the one that sounds like a complaint, why does America have to wait until 2044? The answer is that America is not waiting for a new eclipse. America is waiting for its turn on the wheel. The eclipse that skips the United States next week is the same eclipse that will land on Montana in 18 years. It is not similar to it. It is not comparable to it. It is the same member of the same family, one revolution of the pattern later. And the reason it lands on Montana rather than Iceland is that the Earth will have turned another 1/3 of the way around before it arrives. There is an obvious follow-up here, and it is the one I would ask. If each step is 1/3 of the way around, then 3 steps should be a full lap. 3 Saroses, 54 years and about 33 days. And unlike the Saros, it is a whole number of days, so the eclipse arrives at the same time of day on the same side of the planet. Except the circle does not quite close. 3 steps of 97 degrees, 97 degrees, and 95 degrees comes to 289. A full lap is 360. The family does not return to where it started. It falls short every single time, and the shortfall accumulates. So a Saros family does not orbit the Earth in neat laps. It crawls round and round, never quite closing the loop, gradually working its way through every longitude on the planet over the course of its 1,000-year life, which is why Saros 126 has, at various points, thrown its shadow across Egypt, the Pacific, Siberia, the Atlantic, and the Midwest without ever repeating itself. And there is a second drift running alongside it, which is the one that matters more. You've already met it. It's Gamma, the number that measures how far the shadow axis sits from the center of the Earth, climbing from 0.83 in 2008 to 0.90 in 2026 to 0.96 in 2044. While the family walks west around the planet, it's also climbing north. Every member of Saros 126 arrives a fraction higher than the one before it because the moon crosses the node a little further along its orbit each time. 18 years, 11 days is close to a perfect repeat, but it is not perfect, and the small error does the same direction every time. So the family is doing two things at once: turning through longitude, which decides which country stands underneath, rising through latitude, which decides whether there is anything to stand under at all. The turning is what gives Montana its date. The rising is what will take it away. Because here's what that northward climb has already cost. In 1990, this family put the sun 40 degrees above the horizon at greatest eclipse. In 2008, 34 degrees. Next week, 26. In 2044, over Montana, 15. And the totality is shrinking with it. 2 minutes and 33 seconds in 1990, 2 minutes 27 in 2008, 2 minutes 18 next week, 2 minutes and 4 seconds in 2044. Every member of this family is a slightly worse eclipse than the one before it. Lower sun, shorter darkness, further north. It's been getting worse in the same direction at the same rate as long as anyone has been keeping records. But this family has not been dying. Something that has been running since 1179 had a middle, and it had a best. And when Saros 126 was at its peak, it did something over the United States that hasn't happened since and will not happen again. On the afternoon of the 8th of June, 1918, the moon's shadow crossed the entire United States in 47 minutes. It made landfall near South Bend, Washington, ran down through Baker, Oregon, crossed Denver, and finished at Orlando, Florida as the sun was setting. It was the last time totality crossed the nation from the Pacific to the Atlantic until the 21st of August, 2017. 99 years between those two events, almost exactly a century in which the shadow never once made the full crossing. The country took it seriously. The United States Naval Observatory sent an expedition to Baker City, Oregon, funded by a special grant from Congress. Astronomers traveled from across the country. The whole apparatus of American science pointed itself at one afternoon in eastern Oregon. And on the morning of the 8th, the sky closed over. S.A. Mitchell, director of the Leander McCormick Observatory at the University of Virginia, was standing in Baker City when it happened and wrote about it afterward in the New York Times. Soon after 3 o'clock, he said, the clouds became denser and so black that the whole sun was blotted out. The hearts of the assembled astronomers sank. By 3:45, the cloud had thinned enough to see the corona. Photography in 1918 could not capture what the eye could see. Film could record the shape of the corona, or it could record the brightness, and not both. So the plates came back looking nothing like the thing people had stood outside for. Which is why the American Museum of Natural History had hired a painter. Howard Russell Butler was an artist who had trained in physics. He had developed a shorthand system for recording color and structure at speed, and he used it that afternoon on the corona of 1918. He had 112 seconds to work with. The painting he produced afterward from those notes is still the best surviving record of what that eclipse actually looked like. And all of this happened while the country was at war. Coverage of the eclipse was a brief respite from news of the World War that dominated the newspaper pages. Between casualty lists and troop movements, a few inches of column explaining that the sun would go out over Denver at tea time. Now, here is why that afternoon belongs in this film. The total solar eclipse of June 8, 1918 is number 42 of Saros 126. The same family, the same 1,000-year lineage, 6 members before the one arriving next week. 1918, America. 1936, Central Asia. 1954, Scandinavia. 1972, Alaska and northern Canada. 1990, Finland and the Soviet Arctic. 2008, Siberia and China. 2026, Iceland and Spain. The eclipse that skips the United States next week is the same eclipse that gave the United States its only coast-to-coast totality of the 20th century. It has simply walked around the planet 6 times, a third of a turn at a stretch, and drifted north while it did it. But there is a second problem here, and it is worse than a wait. Look at what this family used to be capable of. In 1918, the shadow axis passed just halfway from the center of the Earth to its edge, a gamma of 0.47. The sun sat 62 degrees above the horizon at greatest eclipse, high and clean, and the umbra came down almost square onto the surface. The path was 66 miles wide on the Pacific coast and 40 miles by the time it reached the Atlantic. Narrow because a shadow arriving straight on makes a small, tight footprint, and totality ran 2 minutes 23 seconds in the middle of the country, in the middle of the afternoon, over Denver. Now, 2044. Gamma of 0.96, 96% of the way to the edge of the planet. The sun 15 degrees above the horizon, close to setting. A path 281 miles wide, which sounds better and is not, because that width is the signature of a shadow arriving at a slant and smearing across the curve. Totality, 2 minutes and 4 seconds. Same family, same moon, 126 years apart. In 1918, it crossed 1,400 miles of American mainland at high afternoon. In 2044, it will clip the top edge of Montana and the Dakotas at sunset and be gone. This family is not returning to America. It's leaving, and it happens to pass over Montana on the way out. Which brings up the thing I've been circling since the beginning. 72 eclipses, 1,280 years. A family that has been running since before the Magna Carta and will still be running 400 years after everyone alive today is gone. And in all of that, exactly 10 of them are total. 10 out of 72. 1918 was 1. Next week is 1. 2044 is 1. So what are the other 62? And why does a family that spends 12 centuries throwing shadows at this planet only manage to blot out the sun 10 times? The answer is that Saros families are not fixed things. They are born, they mature, they weaken, and they die. And this one is very close to the end. On the 10th of March, 1179, a shadow grazed the sky above the southern polar ocean and blocked 5% of the sun. Nobody saw it. There was nobody there. And that was the birth of the family of eclipses that will cross Iceland next week. This is how every Saros family begins, not with a spectacle, with a near miss. Think back to gamma, the number that measures how far the moon's shadow axis sits from the center of the Earth. 0 means dead center. 1 means the very edge. Above 1 means the axis misses the planet entirely. Ceros 126 was born with a gamma of -1.54. Well past -1, the shadow axis was not just off the edge of the Earth, it was a full half-planet clear of it. Only the outermost fringe of the penumbra caught the southern rim, which is why the sun dimmed by 5% above an empty ocean and nothing else happened at all. And then it started to climb. Each new member, 18 years and 11 days later, arriving with a shadow axis a little closer to the center of the Earth, -1.49, -1.43, -1.37. 8 members in the eclipses were still partial, still polar, still unremarkable. But the shadow was walking north across the face of the planet, and by the 9th member, it had arrived. The 4th of June 1323, the first central eclipse of Ceros 126, and it was annular. Annular, not total, because at that stage in its life, this family was firing while the moon sat toward the far end of its orbit, too small in the sky to cover the sun completely. A ring of light around a black disk, no corona, no stars, a bright day with something strange in it. And that is what this family did for the next 5 centuries. 28 annular eclipses in a row, 487 years, rings of fire over the Pacific, over Africa, over the Atlantic, over places that had no written astronomy and places that did, all the way from 1323 to the 4th of April, 1810. Then something shifted. On the 14th of April, 1828, Ceros 126 produced its first hybrid eclipse. A hybrid is an eclipse that cannot decide what it is. The Earth is round, so observers at the middle of the track are slightly closer to the moon than observers at either end. And for a narrow window, that difference is enough. The eclipse begins annular, becomes total for the middle of its path, and turns annular again before it finishes. 3 hybrids over 36 years, 1828, 1846, 1864. The family standing exactly on the line between one kind of eclipse and another. And on the 17th of May, 1882, Ceros 126 turned total. That is the beginning of the 10. 1882, 1900, 1918 over America, 1936, 1954, 1972, 1990, 2008, 2046, next week, and 2044. 10 total eclipses, 162 years from the first to the last. That's the entire window in which this 1,200-year family was capable of blotting out the sun, 12% of its life. And here's the part I find hard to get past. Photography was invented in 1826. This family produced its first total eclipse in 1882, which means every single total eclipse Ceros 126 has ever produced has happened inside the era of the camera. There's a photographic record of all of them. There will never be one it did not photograph. For 487 years, it threw rings of fire across a planet that could only draw them. Then, in the century it learned to make coronas, we happened to be ready. But look at what the climbing did. 1882, gamma 0.33, sun 71 degrees up the sun. 1900, gamma 0.39. 1918, gamma 0.47. 1936, gamma 0.54. 1954, gamma 0.61. 1972, gamma 0.69. 1990, gamma 0.76. 2008, gamma 0.83. Next week, gamma 0.90. 2044, gamma 0.96. The same steady march that began in 1179 with the shadow half a planet below the southern rim has carried it up across the whole face of the Earth and is about to carry it off the northern one. The family did not choose to be total for 162 years. It was total as long as it took to walk past the middle. Everything before was a ring. Everything after will be nothing much, and the corona was what happened while it crossed. That's the shape of a Saros family. Born at one pole as a graze, annular through its long approach, hybrid for a few decades on the boundary, total across the middle and then out the other side. 8 partials, 28 annulars, 3 hybrids, 10 totals, and 23 partials, 72 eclipses. That's the whole life of Saros 126 written out. Read the last number again. 23 partials after the totals end. There are 2 totals left, next Wednesday and 2044. After that, this family will produce 23 more eclipses across 415 years, and every one of them will be a partial. If you want to see what those last 2 look like and what happens to Montana on a Monday evening in August 18 years from now, that's where this film goes next. It's the whole reason the 2044 date is worth caring about, and it's the last chapter of a story that started in the 11th century. So let's go there. 22nd of August, 2044. Great Falls, Montana. Sun, 15 degrees above the western horizon and dropping.
Monday, the 22nd of August, 2044, 17 minutes past 7 in the evening, Mountain Daylight Time, Great Falls, Montana. That is the appointment. 18 years, 11 days, and 8 hours from next Wednesday, and it has been on the books since before anyone reading this was born. The track begins over Greenland, as this family's tracks now do. It runs southwest across the Canadian Arctic, through Nunavut and the Northwest Territories, down over Alberta and eastern British Columbia, and crosses the border into the United States in the late evening. In the United States, the path of totality crosses Montana, North Dakota, and Dickinson. It passes over Great Falls, Montana, and Williston and Dickinson in North Dakota. 3 towns you have probably never had reason to think about, and 18 years from now, they will be the most photographed places in the country for about 90 seconds. One piece of housekeeping first, because it causes genuine confusion every time this eclipse is written about. The catalogs list this eclipse as the 23rd of August, 2044. Astronomers work in universal time, and greatest eclipse happens at 17 minutes past 1 in the morning on the 23rd is universal time. Montana is 6 hours behind that in August, so on the ground in the United States, this is an evening event on Monday the 22nd. Same eclipse, 2 dates. If you are booking anything, book the 22nd. For what it is worth, that makes 3 in a row. August 21st, 2017 was a Monday. April 8th, 2024 was a Monday. August 22nd, 2044 is a Monday. The universe has no opinion about the working week, but American employers are going to have one 3 times. Now, what it will actually be like. And this is where 2044 stops resembling anything most Americans have experienced. Start with the sun. At greatest eclipse, out over northern Canada, it will sit 15 degrees above the horizon. 15 degrees is roughly the width of your outstretched hand, arm's length, held sideways. Low. And Montana and the Dakotas are further along the track than that. Later in the evening, closer to the end, the sun there will be lower still. Which means nobody in the United States will be looking up at this eclipse. They will be looking sideways, out across the plains, into the west, at a sun already in the thickened orange air near the horizon. And that produces something genuinely unusual. In a high sun eclipse, like 2024, the corona appears in the sky that has gone blue-black all the way around, with a band of twilight color at the horizon in every direction. You are standing under a shadow 100 miles wide and seeing daylight beyond its edges on all sides at all once.
A sunset eclipse does not do that. When the sun is nearly done, the sky is already doing half the work. The corona will appear against a sky that is not black, but graded, blue above and burning at the bottom, with the silver of the corona sitting directly in the color. There are very few good photographs of this in existence, not because it is impossible, but because a low sun totality requires an unobstructed horizon, clear air along a very long line of sight, and the willingness to travel somewhere that has all three. The northern plains of Montana have an unobstructed horizon for as far as anyone can see in any direction. Second thing, the path will be wide, 281 miles across against 183 next week and about 70 in 1918. That sounds like good news, and it is not, and the reason is the thing from earlier with the torch. A shadow arriving straight on makes a tight footprint. A shadow arriving at a slant smears out into a long ellipse. 2044 is wide because it's grazing, and grazing is also why it's short. Because the third thing is the duration. Maximum totality 2 minutes and 4 seconds, and that maximum happens over in northern Canada, not over the United States. By the time the shadow reaches the northern plains, it will have shortened. Roughly 90 seconds is the realistic figure for the American section of the path. 90 seconds after a 20-year wait. For comparison, 2017 gave the United States about 2 minutes and 40 seconds at its best. 2024 gave 4.5 minutes. 2044 gives a minute and a half at sunset in 3 states and only if the weather holds. And the weather is worth being honest about, because late August on the northern plains is not simply a good bet. The climatology is genuinely favorable. August in Montana and the Dakotas is dry, and the odds of clear sky are among the better ones on offer anywhere in North America. That is real, and it is the strongest thing this eclipse has going for it. But late August is also the back end of fire season in the Northern Rockies, and smoke from fires hundreds of miles away routinely settles across that entire region for days at a time. Smoke does not stop an eclipse. It does something arguably worse to a low sun totality, which is that it eats the corona because you are looking through the maximum possible thickness of atmosphere, and every particle in it is in the way. So, here's what to expect if you are standing outside Great Falls on that Monday evening in 2044. The light goes strange early, and stranger than it would be at midday, because sunset light is already odd, and this will be sunset light with a piece missing. Then, in the last minute, the western sky darkens in a way that does not look like evening. The shadow will be coming in almost horizontally across the ground. So unlike a high sun eclipse where the darkness drops on you from above, this one will arrive across the plain like weather. And then the sun, 15 degrees up and falling, goes out. The corona opens in a sky the color of a good evening. Venus will be there. The horizon will hold its light. 90 seconds later, it comes back, and about half an hour after that, it sets properly. And that is the end of America's 20-year wait. It's also the end of something considerably larger, because the catalog doesn't stop at 2044. There are 23 more eclipses in this family after Montana, and the very next one, 18 years later, is where 1,280 years of this thing finally runs out.
0.9749. On the 3rd of September 2062, 97% of the sun will disappear behind the moon. It will be the deepest eclipse the family of Saros 126 has ever produced, and it will be a partial eclipse. Nobody anywhere on Earth will see totality. 97% covered, and the sun stays lit. No corona, no stars, a thin sliver of photosphere left along one edge,
and a sliver of photosphere is enough to keep the sky blue, because the surface of the sun is roughly 1,000,000 times brighter than the corona around it. Take away 97% of 1,000,000 and you still have 30,000. That is the cruelty built into eclipses. There is no gradient at the end. You get everything, or you get a bright afternoon with something odd in the right. 97% is not 97% of the experience. It is 0% of it. And the reason it fails is a number you already know. 2026, 0.8977. 2044, 0.9613. 2062, 1.0912. Above 1. Above 1 means the shadow axis misses the Earth. The umbra, the dark core where the sun goes out, passes over the top of the planet and touches nothing but space. What lands on the ground is only the edge of the outer shadow, the penumbra, and the penumbra never blocks the whole sun. It cannot. That is what makes it the penumbra. So, on the 3rd of September 2062, this family's shadow will arrive at the Earth, aim for the North Pole, and go over the top by a fraction of a planetary radius. That is the end of it. There are 23 more eclipses in Saros 126 after Montana: 2062, 2080, 2098, 2116, 2134, on and on, every 18 years and 11 days, all the way to the 3rd of May, 2459. Every single one of them is a partial, and every single one is smaller than the last. 97% in 2062, 87 in 2080, 79 in 2098, down through the 22nd century, the 23rd, the 24th, the shadow climbing further off the top of the world with every return, until the last member of the family arrives on the 3rd of May, 2459, and shades 2% of the sun above the Arctic. 2%. Undetectable to anyone not specifically watching for it, over the pole, with nobody underneath. The same way it began in 1179 at the other end of the world. So this is the answer to the question this film opened with, and it is bigger than the question was. America is not waiting 20 years for an eclipse. America is waiting for the last total eclipse that Saros 126 will ever produce, and it lands on Montana. 1,280 years, 72 eclipses, 10 of them total, across a window of 162 years that opened in 1882 and closes over the northern plains of the United States on a Monday evening in 2044. 1918 was this family at its best, crossing America at high afternoon with the sun 62 degrees up. 2044 is the same family at its very last, crossing America again at sunset for 90 seconds on the way out of the sky forever. It opened over America, and it closes over America. That is a coincidence. It's a very good one. Now, before this becomes gloomier than it deserves, one correction. Saros 126 is dying. Eclipses are not. There are roughly 40 separate Saros families running at any given moment, staggered, overlapping, each at a different point in its own 1,000-year life. While 126 is walking off the North Pole, others are being born at the South. Others are in their annular centuries. Others are in their totality windows right now. The eclipse of April 8, 2024 belonged to Saros 139, and that family has totals left. The coast-to-coast American eclipse of 2045, 6 minutes of it, from California to Florida, belongs to a different family again. So the sky is not running out. One particular 1,200-year lineage is finishing, and we happen to be alive for the last 2 entries in it. Except, there is a reason I've been careful to say that this family is dying, rather than that eclipses are. Because everything in this film so far has been about geometry that repeats. The Saros repeats, the families overlap and take turns. Nothing that has been described in the last hour is permanent, but all of it is cyclical, and cyclical things come back around. There is one thing in this system that does not come back around. It has been running in one direction since before there were oceans on this planet. It's measured to the millimeter, and it has nothing to do with Saros families at all. Every year, the moon is further away than it was the year before. We know that because there are mirrors on it, left by men who walked there, and we've been bouncing lasers off them since 1969. What those mirrors have measured means that total eclipses are not a permanent feature of the Earth. They are a phase, and it has an end date.
There is a mirror on the moon. Neil Armstrong and Buzz Aldrin put it there in July 1969, and it is still working. The Apollo 11 crew left a panel of corner cube retroreflectors on the lunar surface. Later Apollo missions left more, and so did the Soviet Lunokhod rovers. A corner cube is 3 mirrors leading at right angles, like the inside corner of a box, and it has one useful property. Whatever direction light enters from, it comes straight back out the way it came. You cannot aim it wrong. You don't have to. Which means that for over half a century, observatories on Earth have been able to fire a laser at the moon and get the pulse back. The Apache Point facility in New Mexico and the Côte d'Azur station in France time the returning pulses with extraordinary precision. The beam leaves as a tight column and arrives at the moon spread across a couple of miles of surface. What comes back is a handful of photons out of hundreds of quadrillions sent. And from the travel time, the distance is known to within about an inch. Do that for 57 years and a pattern comes out of the data, and it is not a subtle one. The moon is moving away from the Earth at about 1.5 inches per year, about the rate a fingernail grows. Every year the moon is 1 fingernail further away than it was, and it has been doing that since long before there was anyone here to measure it. The mechanism is the tides, and it works like this. The moon's gravity pulls the oceans into a bulge, but the Earth spins much faster than the moon orbits, so friction drags that bulge slightly ahead of where the moon actually is. The bulge is a lump of water with mass sitting a little in front of the moon, and it pulls on the moon. Being pulled forward means being sped up, and when you speed up an orbiting body, it doesn't go faster, it climbs. That energy has to come from somewhere, and it comes out of the Earth's rotation. So the same process that pushes the moon outward is also very slightly slowing this planet down. Earth's day lengthens by around 1.7 milliseconds per century. Coral fossils and layered sedimentary deposits called tidal rhythmatites preserve the record of Earth's rotation directly, and they indicate the day was about 19 hours long a billion years ago. Now, before this number gets used for more than it can carry, one honest correction. Because there's a trap here, and most retellings walk straight into it. Take 1.5 inches a year and run it backward. Project the current rate into the past, and the moon collides with the Earth about 1.5 billion years ago. The moon is 4.5 billion years old, so the projection is wrong, and it's wrong by a factor of 3, which tells you something important. The recession rate has not been constant. It depends on tidal friction, and tidal friction depends on the shape of the ocean basins and where the continents happen to be, and those have been rearranging themselves for the entire history of the planet. 1.5 inches a year is a measurement. It's one of the most precise measurements in astronomy. It's also a snapshot of right now, and running it forward for hundreds of millions of years is a projection, not a prediction. Keep the two apart. With that said, here's what the projection gives. As the moon retreats, it looks smaller, and the geometry that lets it cover the sun completely is already marginal. It fails routinely today every time an eclipse happens, with the moon toward the far end of its orbit. That's what an annular eclipse is. A ring of fire is a failed totality. For totality to become impossible even at the moon's closest approach,
That closest approach has to grow by something over 22,000 kilometers, which is around 13,700 miles. At 1.5 inches a year, that takes roughly 600 million years. The figure traces to a NASA statement in 2017 from Richard Vondrak, a lunar scientist at the Goddard Space Flight Center, who described a total eclipse as a dance with 3 partners and said that the number and frequency of total eclipses will fall over time until Earth sees its last one roughly 600 million years from now. And the careful sources are clear that 600 is an order of magnitude, not a date. The Belgian astronomer Jean Masse has pointed out that orbital perturbations complicate the picture considerably, and that the system doesn't stop cleanly. Vondrak said something similar himself. It's impossible to predict where the lunar shadow will fall by then, or even where Earth's continents will be. There's a hard edge to this. Fred Espinak's 5-millennium canon of solar eclipses computes every eclipse from 2,000 years before Christ to the year 3000. The last total eclipse in it falls on the 26th of April 3000 over South America, the Atlantic, and North Africa. That's not the last total eclipse. It's the last one anyone has bothered to calculate. Past it, the arithmetic still works, but the uncertainties in the moon's orbit have grown large enough that the answers stop being worth printing. 600 million years is a number no one has intuition for, so try it in the other direction. 600 million years ago, the most complex thing on this planet was a soft-bodied organism lying on a seabed. That's the Ediacaran. No land plants, no bones, no eyes worth the name. Total solar eclipses are a phase this planet is passing through, and we are somewhere near the end. Not the last generation, not close, but total eclipses had a beginning, when the moon first retreated far enough to stop swamping the sun entirely. And they will have an end, and everything in between is the window. Which leaves one question that is smaller than all of this and matters more. That window is open now. It won't be open forever, and it's not open everywhere at once. So the practical question is not how long total eclipses have left, it's how many of them fit inside one human life. The sun is about 400 times wider than the moon. It is also about 400 times further away. That is the whole thing. Every eclipse in this film, every Saros family, the 1280 years of Saros 126, the 1918 crossing, and the 2044 appointment, all of it rests on 2 numbers that happen to be the same number and have no reason to be. There is no physics connecting them. The moon's size was set by an impact 4.5 billion years ago. Its distance is set by tides that have been pushing it outward ever since. The sun's diameter has nothing to do with either. 3 unrelated facts, and they land on top of each other so precisely that the moon's disk covers the sun's disk and stops at the edge, leaving the corona visible and nothing else. No other planet in this solar system gets that. Some have moons far too small, so their eclipses are ring eclipses forever. Mars has 2, and neither is close to big enough. Jupiter's moons are enormous, and their shadows blot out the sun and everything around it, which is not an eclipse, it is a nightfall. The corona is only visible because the fit is exact. Too small a moon and the photosphere stays lit and drowns it. Too large a moon and the corona is covered along with everything else. It has to match, and here, now, it matches. So, the practical question. Pick any spot in America. On the long-run average, the moon's umbra crosses it about 375 years. Nobody's life contains a totality by default. The default is that you are born, you live, and the shadow never once comes to you. Which means every totality anyone has ever seen was, for almost all of them, a decision. Somebody looked at a map, worked out where the stripe fell, and went there. Here are the 3 that are coming. The 30th of March, 2033, Alaska, 7 years from now. Real totality over Nome and the Arctic coast and reachable parts of the state in the last week of March, which in Alaska means cold, low light, and a genuine gamble on weather. The 22nd of August, 2044, Montana, North Dakota, South Dakota. 18 years, 90 seconds at sunset over the northern plains. The last totality Saros 126 will ever produce. And the 12th of August, 2045, coast to coast, California to Florida. That one is the great one. Different family, low gamma, high sun, a path that runs down the middle of the country in midsummer, and totality lasting up to around 6 minutes, more than twice what 2017 gave, and nearly half again what 2024 gave. And look at the date, the 12th of August, 19 years to the day after the eclipse that skips America next week. That one is a coincidence. The calendar has no memory, but it's a good one. So run the arithmetic on yourself. If you are 35 while watching this, you're 42 for Alaska, 53 for Montana, and 54 for the coast to coast. If you are 20, you're 27, 38, and 39. If you are 60, you're 67, 78, and 79, and all three are still on the table. 3 in 19 years, against a baseline of 375. Nobody in American history has had a run like the one currently underway. 2017, 2024, 2033, 2044, 2045. 5 totalities inside 28 years, in a country that by the ordinary run of things should see 1 or 2 in a lifetime, and probably neither. The 20-year gap in the middle of that isn't the drought. It's the pause between 2 of the most eclipse-rich decades this country will ever have. Next Wednesday, the shadow goes somewhere else. It starts at 1 minute to midnight on a peninsula in Arctic Russia. It runs over the pole. It crosses the Greenland ice and clips Reykjavik, and does its finest work over 2 minutes and 18 seconds of open Atlantic, where nobody's standing. Then it comes down on Burgos and Leon and Valladolid in the last of the light, and Spain gets its first totality in a generation, low and orange and strange. Across the northern edge of the United States, a fifth of the sun goes missing at lunchtime, and almost nobody notices, because a fifth of the sun is nothing, because there's no such thing as most of a total eclipse. And member number 49 of Saros 126, which has been arriving on schedule every 18 years and 11 days since the 12th century, which was annular through the Renaissance and hybrid through the 1800s, and total across the sun for exactly 162 years, which crossed this country once already in 1918, while the newspapers were full of the war, will come down out of the Arctic Canadian Arctic on the evening of Monday, the 22nd of August, 2044, and stop over a stretch of grassland in Montana for 90 seconds. And then it will go up over the pole, and it will never come back.
There is a habit in eclipse writing of ending on how small it makes you feel. That is not what the catalog says. The catalog says that on the 3rd of May 2459, at a specific hour above the Arctic Ocean, 2.1% of the sun will disappear behind the moon, and that this will be the 72nd and last member of a family that began in 1179. Nobody will be underneath it. It will not be visible from anywhere anyone lives, and it has been calculated to the minute 433 years in advance by people using 3 numbers the Babylonians started writing down before there was a word for astronomy. That is the actual story here. Not that we are small. That from the surface of one planet, watching one moon over enough centuries, it turned out to be possible to work out exactly where a shadow would fall in the year 2044, and to be right. Great Falls has about 60,000 people in it. Most of them had never had a reason to think about Saros 126. In 18 years, the sky above them will do something it will not do again. And the date has been sitting in a table, waiting for longer than any of them have been alive.
Next Wednesday, look north. Not because you will see anything. If you are in the northern states, you will see a bite you wouldn't have noticed. And if you were anywhere else, you will see nothing at all. Look north because the shadow will be up there, moving over the pole at 3,000 miles an hour on its way to Iceland and Spain, and then 18 years and 11 days later to a field outside Great Falls, Montana at 7 in the evening for 90 seconds. It is already on its way. It has been since 1179.